Okay, welcome to lesson 3 on the normal distribution. We're looking at the normal curve. So we've actually kind of been leading up to this fact that we can get this curve called the normal curve. And this quote from Francis Galton is just kind of saying how important this curve is. When things are chaotic and they seem like you can't measure them or predict them, there is this normal curve that happens for many natural things, almost all natural things, um, but also man-made error, such that like we can predict that there's and we can expect that there's going to be this certain normal or mound-shaped distribution. Manufacturing is a big part of this, and so we actually know that we can expect some things to fall far from the average, and so we're going to look at what that looks like. This is a Galton board, so I'm not going to show this video, but you can look at it yourself. You can just YouTube search Galton board, or you can click this one from the PowerPoint. And so again, it's just this idea that like if we got this natural occurring thing, we're going to predict where the balls are going to land. And this actually ties to the binomial distribution. And so the binomial, when you have a 50% chance on both sides of success and failure, you get this normally distributed object or normally distributed curve. So you can think of like a bunch of things that are naturally occurring, continuous variables that would take that shape. So the learning goal is we're talking about how the normal distribution often models the frequency of continuous random variables, and we're going to use it to calculate probabilities. So characteristics of the normal distribution, display a normal distribution, so quickly draw one. I can calculate simple probabilities as well. And so the law of the frequency of error that Sir Francis Galton mentions really is just this idea that we can predict when we do have a like kind of law of large numbers kind of thing, how things deviate from the average. So the normal curve is saying that like we can assume that the modal interval is right in the middle, and then as you get further from the average, you're going to get lower objects. And so if you look at like the mass of potatoes, for example, say a company produces potatoes and they measure them and say the average mass is 150, standard deviation is 20. They don't necessarily measure them all, they're just measuring a sample of the population to get those numbers. And then say like, okay, we've got like any potato, so we might produce like hundreds of thousands of potatoes, and I don't know if that's realistic, but we can start to like describe things based on that sample. And the sample might be 21,000 just to represent like the machines and the potato, or sorry, the weight of potatoes in the future. So for 21,000, if we use an interval size of 10, we get this curve. And so the polygon from the last lesson is actually drawn through the middle of these bars, but this red curve is actually the normal curve. And so like the polygon would actually be drawn a little bit more jagged than this. But you can see those gaps where you're saying, well, if the area under the curve is like the area of the rectangles, and that would look almost right, there is some wasted space there. And if you go 5, then you can see the area of the curve going through the middle of those gaps. Still some wasted space. If you go 2, you start to see that this curve approximate the data a little bit better. And 1, it's almost really exactly following, just a little bit higher in different spots. But you can see that there's certainly less wasted space. And that's with actually like random data that's used here to like show this normal curve. The rule of 68, 95, 99.7 is saying that we can predict some probabilities. And so when we got something like this, which is the curve without the histogram part, we can say that no matter the context, there's some things, if we have the mean and the standard deviation, there's things that we know. And the mean and standard deviation customize the curve. For every normal curve, we can say that 68% lie within 1 standard deviation above the mean, or from the mean. And so that's 130 to 170. If we called x the random variable, we'd say that x is normally distributed with a mean of 150 and a standard deviation of 20. And we write it like this, where we actually kind of quote the variance here, but the standard deviation is 20. You won't see that a lot, but I do want to kind of expose some people to that notation. So we're saying that x is the random variable, so that we can use x instead of like saying like the mass of potatoes every time. So x between 130 and 170 is 68. We also know that 95 is within 2. So between 110 and 190, that's 95. And this is the rule of 68, 95, and 99.7. So 3 standard deviations above and below is 99.7. In general, this is always true. You've got the mean in the middle, and adding a standard deviation and subtracting one, you know 68, 95, 99.7. And there's a whole bunch of calculations. You can start thinking about putting a puzzle together. There's a whole bunch of other intervals we know just from these 3 numbers. And so here's some questions that we can, here's different intervals that we can calculate that aren't just 68, 95, 99.7. And so what you can also do is come up with a list of some of your own. So what things can you put together? And it's really just when you're counting by standard deviations. So here's some practice. But the main thing that the main challenge here is to actually draw something. And this is probably not that well drawn because it's got scales every 20. I'd actually want to go with a scale every standard deviation to practice this. You get a question like this with the bottle caps. You want to draw a little normal curve with a mean of 2.8 and a standard deviation of 0.03. And so you count by a 0.03. And so when you see things like 2.77 and 2.83, you can say, oh, that's 1 standard deviation, so that's 68%.